All right, so now what I'm going to do is I'm going to open a circuit diagram and let's work in there a little bit. Okay, so it's 10:30. Give me a second to open this thing. Okay, before that, I need to tell you one more thing about the electric potential. So give me 5 minutes on that, then I'll move on to the circuit diagram. All right, so here, so we talked about the voltage, but what it is really. So the, yeah, here. Okay, so voltage, it is also called as the electric potential. So electric potential is the energy per unit of positive charges that would exist at some point in space if a charge was present there. So it's very similar to gravitational potential. So think about like you're standing up on the ground and then you lift up a little bit, like you climb up onto a top of a tree, let's say, and you're gaining like kind of a potential energy when you're going high in the sky. Now, when you drop something from high in the sky, it's traveled down, right? So it's due to the gravity. So that potential energy called the gravitational potential energy. So here in the electric circuits, we call this electric potential, basically that's an energy. So energy per unit of positive charge that exists at some point in space if a charge was present there. So that's how it's get the energy there. So it's depend on the position. Like for example, in the earth, like if you think about the gravitational potential, so you can assume that the ground is zero gravitational and then you go high in the sky, the gravitational potential energy increases, right? So as well, very similar to that, here in the electric potential condition, we think far in the space is the zero potential, and we are bringing it closer to the earth, so we are increasing the potential energy in that. So the electric potential is the electric potential energy divided by a charge. So 1 volt is 1 joule divided by coulomb. So joule is the unit for energy measurements. It doesn't matter, it is gravitational energy, kinetic energy, thermal energy. Energy is measured in joules. So here electric potential energy is measured in joule, and the charge, you know, the unit for charge is coulomb. So 1 joule divided by 1 coulomb is 1 volt. So electric potential is the potential energy divided by the charge amount. So whatever the 1.5 volts in our battery tells us the what is the energy involved in there. So 1.5 volts, that means some 1.5 joules per coulomb. All right, so the now we know about the electric field lines. So you know, like electric field lines start from a positive side to and travel to the negative side of the charge. So here in this picture, it's a positive charge and a negative charge. So electric field lines start from the positive and travels toward the negative. So if we kept a positive charge particle somewhere here, it will travel from positive to negative, right? So there's something that you keep a charged particle in the electric field. So the test charge will travel along the field line. Okay? So it's basically creating a kinetic energy because it's moving, right? So moving energy is kinetic. So when you keep a test charge in between the electric field lines, then the charges will start moving. Now this is a picture of a capacitor. These are capacitors. And here, if you go to inside of the capacitor, you will see two parallel plates in here. So this is a parallel plate. So one side of the plate get positively charged, other side will be negative. So the field lines are from positive to negative. So the electric field direction is from positive to negative, as in this picture. So two parallel, these are metal. So as you see here, one plate is positively charged and the other side is negatively charged. So the electric field is from positive to negative. And here inside there's a uniform electric field. The electric field is not varying. It starts from here and travels towards there. So if we keep a charged particle here, it should travel in the direction of electric field. So here electric field direction is from positive to negative. So this arrangement is called a capacitor. So in a capacitor, there are no charged particles moving inside, but it's create the positive and negative plates beside. So it's keep the potential energy between the plates. So in between these two, there's some capacitance. So it can hold that voltage in there. Here's a picture of a capacitor in a different way. So capacitor is a device that has two plates separated by a small distance, and you can connect it to a battery and make these pieces charge and store energy in there. Okay, so this is a picture of electric field lines, and here now for this one, this is a plus side and a negative side, and if you draw a line like perpendicular to the electric field lines, those are called the equipotential lines. Now in this one, it's a positive charge, so these black color lines are the electric field lines, but these red dotted lines represent the equipotential lines. That means the potential energy in this region is the same. Now if you move a electron or a proton from within this negative red color dotted lines, nothing will happen because it is an equipotential surface. In a dipole, the equipotential lines looks like as drawn in this red dotted line, but these black color lines represent the electric field lines. Now important thing about that fact is getting electric shocks. Now here's the question. So in this figure you see equipotential lines. So here it is 800 kilowatts volts, and this is 600 kilowatts, 400 kilowatts, and 200 kilowatts. And you see this cow is standing in the 800 kilowatt, that cow B. Cow A is crossing equipotential line. So this cow's back leg is on the 200 kilowatt volt line, and the front side is his head is touching this 600 kilowatt line, right? So the question is asking which cow is most likely to be killed? A or
Cow A.
Cow A, yeah, because yeah, that's correct. Cow A, because the potential difference between the front and the back of the cow is large. So there will be a current flow through the cow A, and that will make a big damage to the cow. But for cow B, the cow B is standing in the same electric potential line. So there won't be a current going through it because there's no potential difference for the current to flow through. Okay, so maybe you have seen birds standing on the current wires, like high voltage current wires, but they never get electric shocks, right? But I don't know, here it's very rare because we don't see a lot of electric lines in the air. Most of the electric lines are grounded. But in my country, we have a lot of electric lines that go in the air. So the bats, when they travel, they touch the two wires of the electric lines. So then they will get burned up by the morning. So they get electric current or the shocks by touching the two different voltage lines. Okay, otherwise, you should not get an electric shock if you are standing up on the same potential line. Okay, now one thing. Now, if you get a car accident onto electric lines, then you should never touch the car and put your leg onto the ground. Then you are making a path for the electrons to flow through. So you will get an electric current going through your body. So whenever you hit a electric line or somewhere that it has electric charges flowing through your car or anywhere, then you should not make a path that electron can pass through. So you need to standing up, or in that situation, like when the car is hit on a electric fire line, then you should not touch the car and jump onto the ground, but you should take your both hands and both legs together and jump out from there and standing up on one location. Okay, then when you, even when you are walking, the current might be going through the ground, so it might make a current flow through your body. So you should take very small steps going away from that electric lines. So that's a precaution or safety thing that you can follow. All right, so let me close this. And quickly, let's work on this. Where's my, okay. I'm going to spend only about 5 to 6 minutes on this. But if you have time, you may play with those circuits. Those who are in the lab, we will be using these circuits to study circuits, different type of circuits. So this is a simulator that we can do the circuit. So here's the wires. And let's say I'm using a, let's use a AC voltage here. And then I need a bulb. Okay, so in this one, the bulb is nicely round. So here, this is the touching place and this is the other side of the filament. So we have to connect wires into these two sides. And maybe let's use a capacitor. Okay, so let's connect all these and let's use a switch as well. So here's a switch so I can control the circuit. Here's, I connected it here. And here's the wire. So I will put the bulb in there. And the other side of the bulb should connect it to the capacitor. This is a simple circuit that I'm making. Here. All right. So in this circuit, I have an AC circuit. So AC, you know, like it's the voltage is frequently changing. And here's a switch that I can close and open. It's a bulb and a capacitor. Now in the second circuit, I need to have a, I like to have a just a DC battery and a bulb. And some connecting wires. So I'll put the battery here. So it's identical with the top one. Okay, here's that, and here's the capacitor that I going to connect with the battery here. I mean the bulb, and then here's I connected with the circuit here, and here's the. All right, now here, the difference between these two circuits is this one powered up with the AC generator. Here, I'm using a DC current supply. So it's like a AA battery. Here, this is the alternative current source. Now, I can use a current chart here. So I'm going to measure the current going through, let's say, this circuit. And also here, I'm going to measure the current that going through this circuit. All right, so let's see. I'm going to close this circuit. Now you see on the diagram graph, there's no current flow through it. So I have to close the switch here. All right, see the variation of current flow through the circuit. It is an AC circuit. So that's why it switches the direction. See, the current is switching the direction. This shows the electron flow. At one point, the electrons goes into the right direction. Other point, it goes to the left, right? Now here, I can even change the frequency of the supplier. So change the frequency. So let me change it to, now it's 0.5 Hertz. So the separation is 0.5 Hertz for a one loop here. But if I change it to 2, now look at how close it's changing. So it's really quickly changing. Now this variation of, you can even watch that from the variation of this brightness of the bulb, right? So that's the AC current. Now think about it. So this is 2 Hertz, but in our household, it's 60 Hertz. So it's quickly changing its current variation. All right, now here, this is a DC circuit. Okay, so let's watch that. Okay, so bulb lights up, but it's going off at one point. Why is that? Look at this capacitor. It's fully charged, right? It's fully charged. So that's why it's the current stopped flowing in the circuit. Again, let's open this. Nothing will happen. But here, look at this capacitor. It's keep charging, discharging. Charging, switching the direction. Charge, switch the direction, right? So that's why you see continuous flow of current here. But for this one, it's not. It's stopped because capacitor is fully charged now. Now I can use the capacitor as a power source. So I don't need a battery anymore. I can simply connect this and let the current flow through it. So I will remove the battery and I'll connect it here. And I close the switch. Oh, come on. Close, close, close. Yeah, close it, please. Yeah, current. Okay, now see, the light again lit, but we are losing the energy on the capacitor. All the charges get used to flow the current through it. Right now it's fully discharged, so we don't see the brightness of the bulb. Okay, so I will send the URL for that simulator. If you have time, you may try drawing the circuits in there and play a little bit. Yeah, those are called PET simulators. PHET simulators. And on that, you can find a lot of simulators, not only physics, but chemistry, biology, and all the others. So you may try using those simulators to study some concepts. All right, so I would call this the end of the day. So if you have any questions, please stay in the meeting. Otherwise, you're good to go. And I will post the lectures. I'll check the settings if it is private already. All right, so I'll see you on Tuesday. Please stay tuned to announcements that's come through the Canvas.
Thank you.
I have a question.
Yes, what's up?
Do you have any like recommendations for alternate websites that we can use to study? Like that's not the PowerPoints.
Okay, I can give you some, but I don't need to make you confused having a lot of resources because we are really concentrated on to few pieces here. But you can watch the PBS crash course for physics.
Mm-hmm.
That's a good one.
Okay.
Because, you know, like this is a conceptual class, so we are not going in detail about calculation and so many high level concepts. So I don't like to put you in a mess, like learning high. That's
right.
Thing. But PBS crash course for physics is a good one.
Okay, thank you.
Thank you.
I have a question, and it's from the electricity part 4 PowerPoint.
Mm-hmm.
It's like, let's see, the 27th slide, where it's like asking how much current passes through each light bulb. Oh. I understand like how to do the first one, but then there was the one where it was asking about what is the equivalent resistance of the parallel combination on the 28th slide. It's on the 28th.
This one? This. So section. Are you good with this one?
Oh yeah. That one, and then the 30th slide.
This
mine. I don't know why mine's different.
Mine is different because I put another slide for announcements, so that's why it's messed up a little bit.
Oh, okay. So yeah,
for you don't see that slide. That's it. Okay, so you want to talk about?
So I was wondering why, like, you have to like add the resistant 1, resistant 2, resistant 3 for this slide, but then the 29th slide, you don't have to do that. You just divide it.
Okay, here's the thing. Here, this question is different from this one. Here, what is asking is how much current passed through each light bulb.
Mm-hmm.
Okay, so you can simply, let me see, shape, okay. So here you see one loop here, right? So it doesn't matter if I cover this up. So there's one loop that go through the bulb and the battery.
Okay.
And then you can cover the middle one here.
And then there's one.
So now you have another loop here, right?
Okay.
Okay, so let's forget about the middle section. This is good, right? Because it's a go through the bulb and the battery. So here there's only one resistor and the bulb.
Uh-huh.
right? So you can simply calculate that current go through the bulb by looking at the voltage across it and the resistance.
And so
But if you want to do, hold on, if you want to do the same calculation, like finding the total resistance and find the voltage, you can do that as well. So you can take the total resistance of this parallel. So it will be 1 over 10, 1 over 10 over that. It's 0.1, 0.1, 0.2, 1 over. Then you can calculate it. That's a lengthy way to do it. We don't need to mess up ourselves. So here we simply look at like what is the voltage across the battery. We can simply read it as 6 volt. Sorry, what is the voltage across the resistor? So you see that the resistor is connected directly to the battery. It's 6 volt. So 6 volt across the resistor, and the resistor is 10 ohms. So you can simply use the Ohm's law to calculate that.
Okay, and then it has the delta V over R. Usually for the delta, don't you have to like subtract something, the difference?
It's the voltage difference. Here, when it says 6 volt, one side is 0, other side is 6. So
one side is 0?
Yeah, 6 volts means the voltage delta V is 6.
Okay, so I don't have to like do it.
No, you don't need to subtract. No. In a battery, this side is 0, this side is plus 6.
Oh, okay.
So the difference is itself is 6 volt.
Okay. And then the next slide, it's asking for resistance.
So it's asking for the total resistance in the circuit. Right? So first thing you need to understand that this circuit is a parallel circuit. So the equation that we are using is this equation.
Yeah.
Okay.
And then you just repeat
until this point, right?
Mm-hmm.
Yeah. Then after that, what happens?
You have to flip it.
Flip it, because 1 over R is equal to 1 over 5. So to find whatever the R, you need.
Oh, okay. You're right. Okay. And okay. So I had like a question from last class too, and it's like with the PowerPoint part 3. Let's see. And it was like slide 9, I think.
Can you find it from your side and then you can share your screen?
Yeah, I can share it with you.
Okay. Is there anyone who has a quick question about something else?
I have a question. How many questions are on the exam?
About 30.
Oh, okay. And they're almost...
It's about 1 hour, so I won't exceed 40 for sure. So 30 to 40 something.
Okay, I'm just wondering. I'm like...
Yeah, it's all going to be multiple choice.
Okay, thank you.
It's very similar to the question that we did in the class and the homework.
So like review top hat questions and review the PowerPoint questions.
Yes.
Basically. Okay. Thank you so much.
And also I'm posting another homework, so you may try that as well.
Oh, true. Yeah, I'll do that for sure.
I had a question. So I'm in your lab class on Monday at 12. I was just confirming we don't have class on Monday.
No, it's Labor Day, right? Yeah, no class.
Okay.
It's schedule, no lab.
Okay, I was just confirming because I know my bio class is still having lab, so I wasn't sure.
For the first lab and the second lab section, I forgot to announce it. But for the third lab section, I did announce that.
Okay.
An announcement through the Blackboard.
Thank you.
Jennifer, do you have that?
Yeah. Do you want me to share my screen now?
Yeah, you may. Is there anyone who has a quick question for some? Because I see 9 of you are waiting here.
Okay, I have a question.
Yes.
So for Tuesday, are we gonna have like a review class, or are we gonna learn more information?
Yeah, I am planning to move on to the next topic. But if you bring questions, I will spend a little bit time on that.
Okay, thank you.
I have a question.
Yes.
For the homework, you will take the highest grade or the last grade?
Highest grade.
Okay, thank you.
It's the first one, so I'm very flexible with that. Okay, who's next?
Do you want me to share my screen?
Oh yeah, you may do that.
All right.
I have another question. Is that okay?
Is it a quick one? Because we're going to go over a PowerPoint slide.
Yeah, it's about the homework.
Yeah, go ahead.
Question number 10.
Uh-huh.
Why the answer is 160 Newton directed downward?
Okay, can you wait for a second because I will go over the Jennifer's question, then I'll come to you because I have to open
Okay.
another. Okay.
Okay.
Sure. Do you see the screen?
Okay. Yeah.
So I get really confused with the scientific.
Okay.
This.
What is the electric field at the location of the charge Q naught due to the other two charges? Okay. This is a continuation of the first question, so they are linked together.
Oh, okay.
So yeah, go for the first one. So you find out the total force there is 9 Newton.
Yeah.
Okay. Now move to the second one.
Um,
You know the force, which is 9 Newton, and you know the charge Q naught, which is 4 microcoulomb. It's given on the first question there.
it's
Yeah.
like
Q
this
naught
right here.
Q naught is 4 microcoulombs. Yeah. So you use 9 Newton and 4 microcoulomb to calculate the value there. So go to the slide 8. Yeah. See the equation? E equal F over Q naught, right?
Yeah.
Yeah, so the force is 9 Newton and Q naught is 4 microcoulombs. Micro means 10 to the power minus 6.
Okay, so since it says 4, I just multiplied right here by 4. That's it.
It's 9 divided by 4.
Yeah, 9 divided. But when I like plug this part in, I'll just put 4 in instead of 1.
Yeah, it is 4 because 4 microcoulombs is
Okay.
the value.
And then how would I be able to plug this in the calculator?
Calculator? Okay, it's depend on which type of calculator you have, but if you're using your phone calculator, you need to go to the scientific notations.
So I have like the scientific calculator. It's like the TI-30XS calculator. Would that work?
Yeah, it should work. But let me find calculator here on the computer. Then I can show you. Oh, good. This is calculator. Yeah. Okay. So let me share my screen with you. Okay. So this is a computer calculator. So if you do like here, you can change your version of the calculator. So I'm
okay.
And then you see like you need 1, right? Divided by, so you type 1 divided by, in parentheses, I put 4 and times it by, oh, sure. Sorry.
That's okay.
I did a mistake.
Why do you need 1? What I did 9 divided by 4 times 10.
9 divided by,
in
parentheses, you put
4.
Do anything. Let me show you this. So let's say you want to get 10 to the power something. Okay. So in that problem, we need to get 10 to the power 4. So you type 4. And
is it 10 to the power of 4 or 10 to the power of -6?
Yeah, in our example, yes, I'm just showing you a practice here.
Oh, I'm sorry.
So if you want -6.
Yeah.
Okay. So you get -6, then 10 to the power.
Oh, okay. Oh, okay.
But it's depend on what type of calculator you have. So you should have the same option like 10 to the powers.
Yeah, and I have that option, but when I did 9 divided by 4 times 10
Yeah,
to the
it's maybe
power-
the function that you put in like order of functions.
It gave me like 225
Okay, so let's do this.
million something.
Let's do this. Okay, so I need 10 to the power -6. So I take -6. So -6 and 10 to the power -6 times it by 4, because it's 4 times 10 to the power -6. Look at this equation here. It's 4 times 10 to the -6.
Yeah.
And then I need the 1 over of this. 1 over and
Uh-huh.
times it by 9.
Yeah. Oh, that's what I got. I got 2 million.
So that's correct.
Oh, that's right.
That is correct, but how can we write this one in scientific notation? So here, in your problem, I mean, in the given answers, it's given in like what? What are the given answers? It's 2.25 10 to the power 6, right?
Oh, yes.
Yes.
Two,
So
and
this
then-
is like 1, 2, 3, 4, 5, 6. So if you move the decimal to all the way to the 2 behind number 2 here, so there will be 1, 2, 3,
Oh,
5, 6.
okay.
So it will be 10 to the power 6. But let me do something else with you because there's an easy way to do it.
Okay.
Uh,
And how do you know if it's left or right? To the left or
oh,
right?
it depends on where the decimal is. So when you see 25, okay, text. So let's say this 2, 5. I'm using a different number because I can't remember what.
That's okay. Yeah.
So let's say this is the number. So that means there's a decimal point back here.
Yeah.
Right? Now I need to move this decimal all the way to this point.
Yes, yes. So it's under
So
10. So
1,
it's like,
2, 3, 4, 5, 6. So I'm going to the front. That means it's positive. So this will be 2.5 10 to the power 6.
oh,
This properly. That's the answer for this. Okay. Now
oh,
instead of this, if we have something like, let's say I have point 0.000345, something like that. Then
mhm.
the decimal is over here, right? So you're going in the backward direction to the right. So you need to move this decimal all the way to behind this number 3.
Yeah.
1, 2, 3, 4, 5, 6. So the answer is 3.456
or
times 10 to the power
negative 6.
minus 1, 2, 3, 4, 5, 6. That will
So it says, like you said, it's going to the negative one is going to the right, and then the top one's going to the left. But
Yeah.
for the answer, it says, for this answer, it says D.
okay, let's do that. Let's do that. So you have 9, okay, divided by
'Divided by 4,
4,
10.
it's 4 times 10 to the power minus 6.
Yeah.
Okay.
Yeah.
All right, so that's what we have. So this is equal to, now look at this, 10 to the power minus 6, right?
Yeah.
Oh, this is to the power.
Yeah. I understand.
Okay. Make sure that it's to the powers. So when
Yeah.
you have something like this to the powers, you can take this into the numerator, but when you're taking it to the numerator, this factor, the power factor, will become positive. So this is actually equal to 9 times 10 to the power plus 6.
Oh, okay.
It's, yeah, I thought you guys know that. I'm sorry. Yeah, I should have mentioned it, right? So I won't mess you up this much. I'll give you without 10 to the powers in the exam. So this is 9 times 10 to the power plus 6 because I take this minus 6 to the numerator. Okay. Now I still have 4 here.
4 at the bottom, yeah.
4 at the denominator. Right? Now you can simply do that. But if
Okay.
calculator, you can solve the number and then you make it to scientific notation. So it's easy.
Okay. Yeah, okay. I think I got it. But I feel like, so this, I have this one question. And it says, let's see. For back to the electricity part 3 slide, after the 2.25 times 10 to the power 6, it has the direction it's going, and it says to the right.
Okay, can you open that thing?
And share it with you? Yeah.
Yes, please.
Okay, I'm talking. And it's this one right here. It says to the right here,
Okay.
and then they have right, right, left, left, left.
Yeah. Look at the numbers. Or you first need to know why it is right? So what is the direction of force? You go to the first slide 7, and force direction is to the right?
Oh, like right here, where it says to
Yeah.
the right.
Now think about a tug of war. You know, like tug of war.
Yeah. Yeah.
Yes. So if you look at this Q0 charge, so there's a 10.8 Newton going towards the right, and
Yeah.
0.8 goes towards the left. So which one will win?
This one, because
This one. So to the right?
Yeah.
So the resultant is to the right.
Yeah.
Yes. So we got it. Go to the other
Okay.
one. Now here, electric field is F divided by Q0, and F is to the right, then the electric field should be to the right, because this charge is positive.
Okay. Okay, I see that. Okay. Because it's the biggest one, really. It
Yeah.
follows the biggest one.
Mhm, mhm.
Okay, I think I'm good.
Yeah. Okay. I will not make you more complicated than that in the exam.
Yeah.
I'll give
Okay.
you simple numbers.
Yeah. No problem.
Okay. Now go back to the. Did anyone ask the question about that number 9 or 10 in the homework?
Yeah. Question number 10.
Okay. I can't remember the question. Let me open it. Okay. So what is the question here? Okay, so it's asked number 9, right? Okay, so it says a uniform electric field of magnitude 40 Newton per Coulomb is directly downward. What are the magnitude and direction of the force on negative 4 Coulomb charge placed in this electric field? Okay, so here's the thing. Share screen. Okay, so it says, let's say there's a charge of something. Can you see my whiteboard here?
Yeah.
Okay, so it says there's a 40 Newton per Coulomb downward, right?
Yeah.
So here we have, it says 40 Newton Coulomb is directly downward. So that's the electric field. So we have a electric field. Why this is not letting me do this? Okay, here you go. All right, so draw, I need a charge. So there's a electric field. So there's an electric field goes this way. Sorry, I'm a little bit glitchy over here. So, but let me make it. Okay, so there's an electric field going downward. Okay. So this text. So here's a electric field which is equal to 40 Newton per Coulomb. Okay, so that's the electric fields goes there. So it's downward with 40 Newton per Coulomb. And now we know the equation, the other equation, that's F equal Q times E. Okay, now in the question it says, what are the magnitude and the direction of the force on a minus 4C? So this, whatever the charge here is minus 4C. So this is minus 4 Coulomb. Okay, so that's what's the given in the problem. So this charge is minus 4C. Now we're going to use this equation here. F direction is same as the E direction. because this is F is a has a direction and E has a direction. So if we use this equation, then I have F equal minus 4, because it's minus 4 coulomb, right? Minus 4 times 40 Newton, whatever the 40 Newton per coulomb downward.
Yeah.
So we all agree. So this is equal to minus 160 downward.
Then,
Also you can say this is equal to plus 160 upward. You can get
so that's
negative
because-
and say downward, or you can go other way around upward.
oh, this is for question 9, right?
I simply use this equation. But if you have only positive charge, then it's same as the downward. Okay, what did I do? Here you go. Is
Then
that
what about if the charge was 4 coulomb?
4 coulomb, positive 4 coulomb? All right.
Yeah.
So I'm going to edit this. Okay. So did you take notes?
Yeah.
So I need only to. So I have. So this is going to be 4, right? So it's 4 times 104, sorry, 4 times 40, so it's 160. It will be positive 160 downward because it's already downward. Or it can be negative 160 upward.
Oh, okay. Now I can understand. So downward,
Now take a picture.
downward doesn't change.
No.
Okay. Now I understand
Let
why.
me edit this. So this is negative. Yeah, if this is positive 4.
Okay.
So we have
That-
positive. Okay, now take a picture.
Thank you so much.
Yeah, sure. All right. Is there any other quick questions, Jennifer?
I think that's good. I just wanted to listen just to make sure. Thank you so much.
Yeah, sure.